Okay, guys, today we're going to go over 5.2. We're going to do torques, but with the angles. So we're going to be including the trig part of the torque formula. So force times radius times sine of theta. There's your dad joke of the day. Enjoy. I am going to go forward and start doing some problems. I don't know. There we go. Okay. So the first, I just have a blank screen because I'm just going to draw out one of these situations and we're going to solve it, okay? So let's say I have a post, and this post is got, I don't know, like something coming out here. So it's like a piece of rod, and then you got a string that goes all the way to the end of it. And let's say you got at the end of it a mass that hangs over. Okay, now we need to give all this stuff weights, okay, so some masses. So let's say the mass of this object it's holding is 5 kilograms. Let's say the mass of the board is, I don't know, 3 kilograms. And let's say it is like 2 meters long, okay? So remember the mass of this board would then be distributed right here in the middle at 1 meter. Okay, now we're going to also need to know the angle here. So let's say 30 degrees. And what they'll probably be asking in this is what is the tension in this rod or something, okay? So what we would go about doing to solve for tension is we would notice that it is a torque problem, okay? Now a torque problem, same thing as before. Torques in the counterclockwise are equal to the torques in the counterclockwise direction. Okay, so let's do the clockwise direction first. So stuff going in that direction. Okay, so one of them would be this mass. So it'd be 5. So it's force times radius. Force would be the weight of it, right? Times the radius. So it is 2 meters away from it. Times, now we're dealing with angles here, so times the angle sine of theta. Now in this case, it is applied force in a 90-degree angle from where it is, yeah? So that angle right there is 90 degrees. So if you wrote here at the end sine of 90, that is just 1. So I'd just be multiplying by 1. So I'm going to avoid doing that here. I just don't want to write a whole bunch of trig stuff unless I need to, okay? So other stuff in the counterclockwise direction, you also have the mass of the post that's holding it up. So we're going to do the mass of it is 3 times its radius. So the distance where its mass is from the pivot point. Remember, this is the pivot point. I probably should have circled that at the beginning. Pivot point is right over here. And the distance it is from the pivot point would be 1 meter. Oh, 3 times 9.8, because that's the force it has, times the radius is 1. And it is also 90 degrees from where it is. So I'm not going to put sine of 90. Okay, that's everything in the clockwise direction. Now let's look in the counterclockwise direction. Notice this force is the only thing, the force of this tension is acting in the opposite direction, but it's not perpendicular to its plane at which it's pulling up on. It's 30 degrees from the plane at which it's pulling up on. So we are going to use that trig here. So it's going to be first the force, which will be tension in this case, times the radius, so the distance it is away from the pivot point, which would be, it holds it 2 meters away from the pivot point, times the sine of the angle at which it is applying the force, which is 30. Okay, and then you would just go about solving for t here. So, like I said before, in the other one, I can't bring, if I take down this PowerPoint, it deletes all the drawings I did. So I have to do the math on this instead of my calculator on the computer. So I will tell you what it all comes out to, and you can check it in your calculator here. So the first part there is 98. Okay, so this comes out to 98 plus 3 times 9.8 will be 29.4 is equal to the tension. So 2 times sine of 30. Make sure your calculator is in degrees because we were working with degrees. 2 times sine of 30. And that is going to be, so sine of 30 is just a half. So 2 times a half will just be 1. So I'm going to add up to this side together, 98 plus 29.4. That's going to give me 127.4 equals t times 1. And you would divide by 1, which wouldn't change anything here, giving you 127.4 newtons. Yeah, that's the force that this tension has, 127.4 newtons. Okay, now that's how the first two problems are on the homework. The third problem is a little bit different, okay? So I have it here. It is a little more difficult, okay? And I'm going to walk through it to help you understand it better if you don't understand it now. Hopefully it'll help you out. And then also another one that I will walk through is the last one on there. I want to make sure that you guys know how to do the forces acting on the rod, okay? So let's walk through this one first. A 3.5 kilogram flagpole. Okay, so I don't have that written down here, so let's get my pen out. Okay, so this flagpole, and guys, a lot of people were asking me questions. They were thinking this is a flagpole, like the picture was on its side or something. No, think of this as a building, and this flagpole is coming out horizontally from the building, and you might have a flag hanging down from it, okay? It's not like a flagpole you would see outside in the middle of the cul-de-sac with the flag on it hanging or anything. It's holding it out horizontally. So a 3.5 kilogram flagpole, so this is 3.5 kilograms, is held horizontally by a bolt that is at the base and a cable attached to the end as shown. Okay, so we have a bolt here, yeah, at the base of the building and the flagpole. And the cable makes a 40-degree angle with respect to the horizontal flag. The flagpole is 1.3 meters long, which is shown, and its mass is distributed uniformly throughout its length. What is the magnitude of the vertical component of the force acting on the bolt as at the base of the flagpole? Okay, so what we have here is we have the forces, we have the flagpole's weight going down that way, right? We have the tension pulling up this way, and it wants to know what is the force that this bolt is applying upwards to hold this together. Yeah. Now it's kind of a weird problem. The first thing that you want to do is find the tension. Okay, and let's just find tension first because I know you know how to do that, and then we'll kind of explain how we would break it up because I think it'll be easier to explain once we have tension how to find the vertical component of this bolt force. Okay, so finding tension would be very similar to what we did on the last slide, okay? So the torques in the clockwise are going to be equal to the torques in the counterclockwise, and I am going to use this as my pivot point, okay? So I am using this as my pivot, which is kind of weird because I was asking about the force here, but I'm ignoring solving for the force here right now. I'm going to solve for tension, yeah? And act like this is a pivot. So the force in the clockwise, well, that would just be the weight of the flagpole, which is 3.5 times 9.8 times the distance from the pivot point, which is 1.3 divided by 2, right? Because its mass is distributed in the middle, is equal to, now in the counterclockwise direction is where the tension is working, so we're going to do the tension force times the radius it is away, which would be at 1.3, and since it's at an angle, it would be sine of 40. Okay, and you just work this out and solve for t. Okay, so I will just do this real quick and tell you what the answer for tension is. Okay, it's 3.5 times 9.8 times 1.3 divided by 2. Okay, so the left-hand side comes out to be, here, I'll write it underneath here, 22.295 is equal to this tension times 1.3 times sine of 40 comes out to be times 0.836. So I'm just going to do that divided by the 0.836, and I got the tension in the flagpole. Okay, and the tension comes out to 26.669 newtons. Okay, now that is an answer here. It's the answer D, right? But that's not what we're looking for. They put that answer there to confuse you. Okay, so let's see how we would figure this out based off of having that tension. So that tension is 26.669. Now, newtons. Now, part of that tension is used to pull this thing upwards, right? To hold up the weight of the flagpole, and part of it is used pushing it into the wall. Yeah, and if you wanted to separate this force to figure out those two things, you just multiply it by sine to figure out the vertical. So this times sine of 40 would tell you, and let's do it real quick, 26.669 times sine of 40 would give you 17.143. Okay, newtons. Now, if you wanted to know what part of the tension is used to push it against the wall, you would just multiply it by cosine, right? You could do tension times cosine of 40. And that would tell us 26.669 times cosine of 40 would be 20.43 newtons. Okay, so 17 newtons is used to go upwards, 20 to go that way. Now, so the cable is pulling upwards with 17 newtons of force, yeah? Now, we want to know how much newtons of force the bolt is holding up. Okay, well, if on the right-hand side it's holding up 17.143 newtons, how much force is the flagpole have in a downward direction? So to figure out just how much force the flagpole has, we could do 3.5 times 9.8. And that comes out to 3.5 times 9.8, 34.3. Okay, so that's how much force the flagpole has in a downward direction. And the tension is holding up 17.143 of it. Yeah, so if you wanted to figure out how much this one's holding up, you would just do the 34.3 minus 17.143, and that'll tell you how much tension or how much weight this bolt is holding up vertically. So let's do that. 34.3 minus 17.143. I did it wrong. 34.3 minus 17.143. That comes out to 17.15. So basically, this side is holding up about half of it, and this side is holding up about half of it. And so this would be our closest answer here, 17.2. And that's how you would calculate how much weight the bolt is holding up. And like I said, that's a lot more of a difficult problem than the first two that you did on the homework. I don't know if the AP Physics exam would tack you that hard, but if you understand that one, you definitely can get anything from this type of genre on the AP exam. Okay, last thing I want to do is I just want to do the free body diagram of this rod, okay? Because I think there's stuff that people could miss on here. So, it says that there's a horizontal uniform rod shown above of 0.6 meters and a mass of 2 kilograms. The left end of the rod is attached to a vertical support by a frictionless hinge that allows it to swing up or down. The right end of the rod is supported by a cord that makes a 30-degree angle with the rod. The spring scale is negligible mass and measured the tension in the cord. A 0.5 kilogram block is also attached to the right end of it. On the diagram below, draw and label vectors to represent all the forces on the rod. Okay, so now I know you guys have done a lot of free body diagrams in the past, I'm sure, but this one might do something to trick you. Okay, so I just want to make sure we get all the forces on here. Okay, one that I know you're going to get, I hope, is the tension, okay? And the tension is going to be in the same direction that the string is, yeah? So I'm going to put that, I'm going to label it T for tension. Now there's also the block. So I'm going to have a free body a force for the block, and you can do the force, you can put like a little B or something for block. Okay, now also remember the rod has a force. It's the weight of the rod, right? So let's not forget the weight that the rod has. So the weight of you could put like R for rod there. And those are the three that I hope everyone would get. Now, don't forget about the hinge though. The hinge is also applying force, and we realized that from the last problem we just did, where we were calculating the force of the bolt. Okay, so this hinge is applying force. Now it's applying a force upwards, like we calculated in the last problem, and it's also applying a force outwards because this tension in this rod is pulling it in towards the wall, yeah, or towards the pole. If that hinge wasn't there, this rod would fly that way. So that means that there must be a opposite force going in this direction to neglect that and keep it in equilibrium. So we have a force coming out this way and a force going up to hold this rod in place. So that means that the force vector of this hinge would actually be kind of angled. So you're going to have something like this, yeah? And I didn't mean to draw it so big. My computer's kind of freezing on me. And that's the force from the hinge. I'm going to put like an H for hinge. Okay? And then you should be able to calculate the reading on the spring scale. It's just asking you to find the tension in the cord, yeah? So I want to make sure that you know how to do that for a free body diagram. Okay, I hope it helped out and you enjoyed it. See you later.